Okay, so we're going to look at um, page 9 of your notes. We're going to start out with vapor pressure. We're really going into phase diagrams here, but you need to understand what vapor pressure and boiling points and all that thing actually mean first. So let's look at vapor pressure. We already learned on heating cooling curves, I talked about vapor being reserved for substances that were liquid or solid at room temperature, not a true gas, which was a gas that was a gas at room temperature. So it is the pressure of the vapor that's present at equilibrium with its liquid. So what that means is equilibrium, meaning in balance with the liquid vapor situation. So when we talk about the boiling point, what that's going to mean is you have to overcome the pressure around it for the liquid to escape and become a vapor. So where that point is, that vapor pressure is where that equilibrium is reached between the liquid and vapor, and it becomes a vapor. So vapor pressure is obviously just some easier way of saying it actually is that the vapor, the pressure of the vapor, so just how much pressure it exerts, okay? And the more molecules you have as vapor, the more pressure you have. Well, that was easier said, sorry, I could have done that easier. Liquids with high vapor pressures are what we call volatile. Volatile is when they easily evaporate. So they just fall apart really easily, okay? They usually are going to have, of course, weak intermolecular forces. So a lot of London dispersion substances will just whoop, right away fall apart really easily because they're not strongly held together. So volatile is easily evaporated. Liquids in which intermolecular forces, we're going to call that IMF if we haven't figured that out right now, right, are large. Okay, that means they are strong, okay, in relativity. They have relatively what low, sorry, I almost answered it, vapor pressures because I was thinking about it in my head, right? If they're strong, what's going to happen? They're going to stay together like a lot longer. So they're not going to go into that vapor state. So the vapors are going to be fairly low relationally. Something that's weak is just going to whoop, and we're going to make a lot of vapors. And so the reason that is because the molecules are held more strongly. And so that means when they're held more strongly, then less break into vapor. Now I use the word break, but that's just because I think it's an easier thing to think of, strength. And it's like, okay, I'm going to break apart. Well, they cannot as many because it's held so tightly. We actually are just changing positions and letting free, right? Like the vapor we saw that the molecules from a solid really close to, we're all over. Okay. So heavy molecules move at blank speeds than light ones. We've already talked about this a lot of times, but we do have to remember this. Obviously, you're heavier, you're slower. Okay. And so that means like the backpack, you put a backpack on somebody, if they can move the same speed, the person with the backpack is going to be slowed down. And so produce a what kind of vapor pressure though? Now we're thinking about, so they're moving slower. So when you move slower, we're talking about going from a solid where particles are packed really closely to way apart. When we're a gas, we want to be moving fast. So it is going to be a lower vapor pressure. So you're slower, you're lower in vapor because they're not going to break apart and have as much energy because, again, we're talking about kinetic energy out here too, temperatures and things like that are all involved in that, and they will be lower. So boiling point is the temperature, okay, that point where that temperature occurs, when the liquid phase overcomes. So it has to be at least equal to, but I mean, we start there, equal to or more. Obviously more than we're going to boil right away, right? Phase overcomes atmospheric pressure. So the pressure of what's around it. It should make sense, right? So you've got liquid water. You're going to cook something in a pot on the stove. All right, we've got the water in here. We got the stove turned on. We got transfer going from the stove to the water. And then once this liquid here has enough, it escapes and has enough pressure pushing up to escape that atmospheric pressure that is pushing down. Okay, the atmosphere is pushing down on it. It escapes and then it becomes a gas and goes out into the room, diffuses, it infuses from last chapter, right? So as altitude increases, the boiling point will do what? Well, because going up higher altitude, we're going to have less pressure because the air is thinner. So less pressure actually means what? That the pressure of the atmosphere is going to be less. So the boiling point will lower in higher altitudes. So that's why a lot of people, you look at cooking instructions and things like that, will burn food if you go into a higher elevation. So I know when we used to camp in Colorado, my aunt burnt macaroni and cheese one time because it was like, oh, that boiled a lot faster. So why did it boil faster? Because the atmospheric pressure wasn't as high and you don't have to wait as long and it gets there faster. Okay. And the vapor pressure lowers, of course, because if you're not boiling as fast, then you're not going to have as much vapor because you can't make vapors if you don't boil due to the boiling point decrease. Okay. So we'll say decrease or lowering, whatever you want to write. Okay. So it is going to go down with the pressure of the atmosphere. All right, last little concept we have to do today, we're going to have lots of different diagrams. They can look very different, and this did not copy very well now that I see it, and I didn't get the line perfect there, sorry. But you can have any kind of phase diagram. It's like this. It's different than heating and cooling, where it's a zigzag. This is a phase diagram. It's showing me my phases of matter and where they're going to become a solid, liquid, gas, or change phases. It usually looks like a kind of Y thing like this, but it can be really wonky and go sideways. And okay, there's lots of different substances. Usually this is about what water looks like, but not really, because this is not actually. I just realized this because pressures. They don't even have a unit here. I mean, I would probably say kilopascals maybe because of such large numbers. And down here we have temperature. I don't think these are Celsius. I think they're Kelvin, but you don't know because they don't have units. So it's not a great graph, but I'm just showing you the points of it first. If I expect you to come get a particular temperature or pressure, like I'm going to talk about in a second, I would actually have a better graph for you, okay, or diagram. So anyway, we want to know two main points here. Well, first of all, let me go with this. At the lowest temperature, so we start here at the low temperatures, the biggest area here with the largest amount of pressure increase that we can have is going to stay as solids. So our solids are going to be this very first big area with the lowest temperatures. Yes, there's some vapors that can occur during those low temperatures, but you got to realize the pressure values with that. But so solid, and then we have liquids, usually that's in the middle of whatever it is over here, and then gases have the highest temperatures going all the way out, okay? So we go in a clockwise manner, solid, liquid, gas. Even if it's funky, it's still going to go that way. All right, a couple things to label and talk about. The critical point is a point on the phase diagram at which both the liquid and gas phases of a substance have the same density and therefore indistinguishable. So what they're saying is, and it does say to label it here, so I'm going to go ahead and do that. This right here at the very tip of whatever diagram you have between the liquid and the gas is going to be our critical point. Now, the critical point is where the solid and or liquid and gas, become indistinguishable. What that means is we can't go back. So it's like there's a dotted line just going up from here. And it's saying, you know what? No matter past this point, you cannot liquefy anymore. You are just going to have a gas. Like we can't distinguish. We can't say what it is. Okay? Or go back. Sorry. So it is a liquid. I'm sorry. It is can't go back to a liquid. Wow. I'm just loving it. Now, if I were to estimate the critical point, and you could do this on any graph, like I would say I would give you definitely better things, but we would absolutely be estimating. So it's not quite halfway between 290 and 300. That's only 10 degrees between. So 295, nope, I'd go 296 maybe. Or you could go 297, whatever. Kelvin does not have a degree mark. So I'm going to say it's Kelvin. Again, this is not a great graph. That's our temperature. And then we also have a pressure. So your X and Y, as you're used to, hopefully, reading graphs. And then that is 10,000. I'm going to say it's kilopascals. Again, we weren't 100% sure. So that is a point, which is the critical point. So at 10,000 kilopascals and 296 Kelvin, that's it. We're going to gas. Okay, we're going to vaporize. We cannot distinguish between those phases of liquid and gas. Now, next point is one of the coolest points ever, and I will show you this video in class that is about the triple point because I could never understand this, that they said, you know what, there's a temperature and a pressure at which the solid, liquid, and vapor, or gas, phases of a pure substance can coexist in equilibrium. So when we say equilibrium, meaning balance, okay, or equivalence. And what that means, wow, how can they all exist at the same time? It's actually a point. And on the video, I stumbled upon this, and it's like the coolest thing because now I can see why or how this can happen. So the triple point is always going to be here at the intersection of all three phases here. And again, you can always trace it down to say, okay, we might go at 280. Again, there's always going to be room for a little bit of estimation unless I have it specifically mapped out for you. And then, I don't know, it looks above 4,000. So 5,000 is about the middle here. I'd only go maybe 4,100, okay, kPAs. Again, huge estimation there. But there is that specific temperature and pressure where you will exist in all phases. Pretty cool. Now, they asked us to label a few other things on the directions over here. And one is the normal boiling point and the normal melting point. So we already got triple point, we got critical point, okay? So normal doesn't really mean anything special. It does in a way, but at standard pressure is all this means, okay? What is standard pressure? Well, now this one's going to be a little bit tough on this graph since standard pressure is 101.325, so it's way down here. So this probably actually isn't kPAs. I'll probably have to turn the page and show you on another one in just a second. So we trace the pressure over and where it hits the melting, which would happen between the solid and liquid. So this line here, we would choose that temperature and do that. So I'm not going to be able to really tell you here. All right, I'll come back and we will do that later. So I'm going to do that on the other page, next page, so I can show you one that actually makes sense. Okay. I guess this could be kPAs too. I mean, torr. I don't know. Anyway, 760 would still be way down here and it wouldn't make much sense. But anyway, label the axes correctly. Yeah, we're trying to do that. We really have no idea. All right, so one other thing I'm going to do, so I don't steal it from the other place, is to label the equilibrium lines. You hear this word. What it means is they exist at the same time. Like it's right on that phase change. So if you remember the zigzag, the curve, okay, the zigzag, right where we go through phase change, this is where it'll exactly be solid, liquid, and on that change line, okay? So this line right here, and I'm going to turn it sideways so I can write it, is the solid, liquid, just like it means between the two of them, equilibrium line. So that means at that point we can exist as both, okay? There's going to be an equilibrium or balancing between them. All right? Then, of course, this is not hard. The liquid to vapor or gas, this is the liquid vapor or gas, whichever word you want to use, and it should depend on the substance. Since we don't know what this is, I'll just write gas. So this is the equilibrium line. So again, if we exist along that temperature, pressure, anywhere, exact ones, we would have a liquid and gas at equal parts, okay? And then right here, we actually do have this line also. So let me go back also. This is where melting and freezing occur, right, between the solid and the liquid. And then this is where boiling and condensing, depending on which way you're going, taking heat away or adding it. And then this one here is the solid, and you guessed it, gas or vapor, equilibrium line. That was a big I, sorry. And that is going to be where we are, well, either going from a solid to a gas, so adding heat, and that is, we call that sublimation, going straight from a solid to a liquid. Or it's the opposite, which is going from a gas to a solid, which is deposition, which a lot of people do not remember, but that is a process, okay? So sublimation or deposition. So those are those lines. Now, I can ask you at any point, like, hey, if I'm at 6,000, we'll say kPAs, and a temperature of, let's just say 295, what phase am I in? Oh, I'm a gas because I'm way out here. Now take that temperature down to 260. Hey, I'm a solid. Or maybe right here at 290, I'll be a liquid. So you can have lots and lots of different questions about phase diagrams. So that's why we'll practice a lot on our worksheets. Now I just want to show you and this again did not draw very well. We'll go through some of these questions in class. I'm going to have you guys working on them, not necessarily me going through everything, just again, watching. So we'll fill in those lines. That's an arrow pointing there. It asks you to fill these in, but I'm going to do the normal boiling point and the normal melting point. Now, again, shoot, you know what? It's not real great on here. I wonder if there's some way. Oh, well. Anyway, I'll just go ahead and hold on a sec. Let me see if I can figure it out. Okay, might as well go here because you will have some more practice in your worksheets, lots of them. So I turned to page 12 in the notes, so just going to accelerate forward here. So I had to zoom out a little bit because you see the diagram down here. This one is much better because it's got pressure in atmospheres and temperature in Celsius. And you can see I'm going to have my solid, my liquid, and my vapor or my gas, whichever one you want to use. Okay. It asked me what's the normal melting point and normal boiling point. So we're going to go with that first. So the normal melting point, again, normal means that's standard pressure. So what's standard pressure in atmospheres? It's 1. Okay, this is standard. So what we'll do is we just need to trace this across. Now I will have rulers if you want to, you can use those. But we dot it across and then we're again estimating. Oh, okay. It looks like it comes up right about 100, right? So maybe it's even a little higher, but let's go about 100. I would probably accept, and it's degrees Celsius, all the way from like, I don't know, it looks like, I mean, I don't know if you go lower than 100, but you could, probably 97 to 110 even. I don't know, because it's such big, they're hundreds here. So might even gone from 90 till 110. So anyway, that's how you're going to do that. You just trace it over. You hit the solid liquid where it's going to melt. And when you hit that line there, that solid liquid equilibrium line, you trace that down for the temperature. Then for the boiling point, you just keep on chucking. Okay. And then again, you go down and you say, oh, okay, that's about 400 degrees Celsius. And again, these are estimates. I might go 10 each side and be okay with that. Now, the next question I will just go ahead and address right now because it'll make sense. What is the normal freezing point? Now, freezing and melting are exactly what? Same point. So when I come here, it can go liquid to solid. We're going taking away heat, or it can go solid to liquid, adding heat. They're going to be the same. So this is no brainer. These are the same. So if I had asked you what's the condensing point, that would be the same as the boiling point. Now, when we talk about sublimation and condensation points, they would be on this line, right? And they would be the same. So we'll do lots of practice, like I said, ask questions as needed, and that is it.